whenever you're ready.
Next talk is by Ferrara. If you don't follow this guy online already, you should be. He's a senior architect for NBC Universal. Specializes in object-oriented design, scalability. But he also does stuff with performance and security. And he's very active member of the PhD community. Blog all the time. He's on Twitter. And a former core member of the Dreamland development team.
A while ago.
So everybody give it up for Anthony Ferrara.
Thank you very much. All right, let's see if we can deal with this feedback issue. Hey, no feedback issue. Yay, I like to move. So how's everyone doing this afternoon, actually? I'm normally used to talking in the morning. So welcome to Boston. Today, I'd like to talk to you a little bit about object-oriented programming. And just for a little bit of backstory on this talk, I've given this talk a large number of times, and I've never been happy with it. And I keep thinking I want to shift the focus. So this is a brand new version of this talk that you get to experience for the first time. So let's talk about object-oriented programming. What is an object conceptually? Well, we have this classic view where an object is a physical thing. It's something that you can touch, you can interact with. You model it off of, a cat or a car or something like that. It's this physical object. Your methods are then behaviors or actions on that physical object, and your properties describe that physical object. Does this sound familiar? A lot of beginner textbooks do this. A lot of blog posts that try to teach object-oriented programming talk about it this way. And what you wind up is something like this, where you have this inheritance tree where you have interface animal, then class mammal implements animal, cat extends animal, lion extends cat. This is simple, right? You have code that looks like this, where you make a new lion. Then you make that lion roar. You move the lion around. I mean, this is, at least from what I've seen, a lot of the way that object-oriented programming is taught and the way a lot of people think about object-oriented programming. You have this object, and then you do things to this object, right? Makes sense. It's simple. But is it realistic? If we look at this code again, last time I looked, to make a new lion, it takes 2 lions in about 9 months. Does a lion have a button to make it roar? No. What does it mean for an object to hunt? We know what a lion does, but what does an object do? What is a lion in relation to our application? And the reality is, we don't know. You have to look at this lion class within the greater context of your application. And that may make sense, and it may not make sense. You're always going to have to depend on context. But the question is, does this model work? Is this model realistic? It's very easy to understand because we deal with real-life things every single day. So if I want to tell you about an object, it's a lot easier for me to say, hey, you can pick up this chair. This chair has properties. Let's call this chair an object. But the problem is, it's easy to understand, but it also completely misses the point. It's completely impractical. If you try to build a realistic system of realistic scale using these techniques, you get lost very, very quickly. I mean, if you want to, what is a session? Okay, I know what a session is conceptually. What is a session object? How do I relate that to the real world? You could probably come up with something, but it's not easy. It's not intuitive. So what I'm going to introduce here is what I call the modern view of object-oriented design. There's a number of different ways to describe this. This is one way that I found I think works. So an object is a collection of mostly related behaviors. Method is a behavior, and properties are details of that. So what do we really mean by behavior? Well, the classical view says this object, this lion object, conceptually is a lion. Or this lion object conceptually is a cat. Behavior does the reverse, which is this object behaves as this other thing that we're trying to model. So a session class, a session object, behaves like a session. And then you have a definition of what a session is, and everything works together nicely. Because we're dealing with behaviors, we're not dealing with types. And this gets important in a second. So rather than using these abstract concepts to talk about it like cats and animals and cars and all this stuff, why don't we try to talk about something that you as developers, me as a developer, do all the time. Let's talk about numbers. So let's imagine we wanted to create objects to represent numbers, okay? We have this interface number, and you have a bunch of methods on it. What we're really talking about, and what this interface describes, is the behavior of a number. We don't care how the number is implemented. We don't care how you're storing it. We don't care about anything except the behavior that we're defining. So we take that to a logical conclusion, and you have this interface number, which we just looked at, and then you have this whole tree of subnumber types that we can have, where you have an unsigned long integer inheriting from long, which inherits from integer, and you can get different data types and different values and different sub-behaviors, but everything on this chart behaves like a number conceptually. Except this is a lie, because we really don't need inheritance. We can talk about object-oriented programming using inheritance. I can sit here and talk, but that misses the entire point of object-oriented programming. You can do OOP 100% without using inheritance once. And a lot of people don't realize this, and that's why you get into these really deep trees, and you have frameworks where everything has to extend from this base class. You don't need any of that. All you need is polymorphism and encapsulation. Does anyone recognize those two words? Okay. So let's really quickly go over them. Polymorphism, for the purposes of this talk, there's a number of types, is behavior that's determined dynamically, otherwise known as dynamic dispatch. What that means is the person who's calling a method doesn't know what that method does. It's determined through some other route. So to explain that, we have this procedural code, and this is relating to that number again. Let's say we want to make a function that adds 1 to a number that we get. The body could look something like this. If a is a long, then we have to return a new long. If a is a float, then we need to return a new float. If a is a decimal, we return a new decimal. How many people have seen code similar to this, where you have this big chain of ifs or switches or anything like that? Polymorphism says these are details of that implementation. I don't care about the details. I want to invert that dependency and say, number, you deal with it. That's polymorphism. That entire block of code, now, instead of me manually choosing what I'm doing based on what you give it, I'm telling that integer object, add 1 to yourself. Simplifies things. It simplifies that relationship. So in the integer class, we would have a method that looks something like this, where when you call that add method, we're going to return a new integer that adds 1 to whatever was passed, that adds the number that was passed in. And this is hand wavy on top, but the point is, it's the class, it's the object that's determining behavior. Float, we have a slightly different thing, where we return a float value. Same concept. So now let's talk about encapsulation. Encapsulation, I tried to define this in terms of behavior. It's where the behavior is completely contained within that object. So we could do something like this, where we pull the value directly from the number. And we say, if value is 5, then we're going to do this, otherwise we're going to do something else. Simple, straightforward. Seen this in a lot of frameworks, I see this in a lot of code. Nothing inherently wrong, but not object-oriented. Object-oriented code, we want to tell that object, compare yourself to 5. So instead of getting 5, we say number equals, and then pass it an integer representing 5. And let that object determine how to do equality. And the reason is, if you've ever tried to implement a fixed point decimal, it is a nightmare. It is an absolute nightmare. The efficient way to do it is splitting up two values where you have an integer value and then an exponent to tell you where that decimal point goes. Point being, when you want to compare equality, it's a heck of a lot easier if the decimal can do it for you instead of having to cast back and forth. So now, by encapsulating everything, encapsulating all of that behavior, we're able to actually make decisions and do code the way we want to. Make sense so far? Kind of? No? Yeah.
So you're passing the integer, like when you do an add,
Yep.
you're also creating an object.
Correct.
Who writes code like that?
I do. So the question was, you're passing an integer and then you create a new object. I write code that way. It's a specific pattern called value object, where you never mutate the state of any object. You always return a new object representing that mutation. It's very much a cross between object-oriented programming and functional programming, but it's just one way of doing it. And I showed it here because I want to show the benefits of encapsulating. You don't necessarily have to return. You could add it directly, but there are benefits to both. So behavior, what we're talking about, is determined by an API. And the API is what you external interact with, or what code that's external to the code we're talking about interacts with. And there's a very specific reason that I talk about it abstractly, and we'll get there in a second. But there's two basic types of APIs. There's an interface, which is explicit, which means I'm writing a class, and I, as the author of this class, am saying this is the behavior that this class does. The other method is called duck typing, which is basically me as the caller am giving you this object. I am telling you this object does what it does. So it's the same concept. You're getting type information in both ways, but one is the writer and one is the user of that class, the user of that object. So, fundamental question here. If an object is a collection of behaviors, what is a collection of objects? So at the root level, we have this API that we're calling a method, which is a primitive behavior. It's the most fundamental unit that we can get. A collection of related methods we call a class, right? A collection of related classes becomes a package. A collection of related packages becomes a library. And a collection of related libraries becomes a framework. So now we can see that when we talk about object-oriented code, we can talk about it at the object level, where we talk about an object moving around within the system and how it behaves. But we could also talk about it at the library level, where we can talk about how a library interacts with the rest of the system. Pretty interesting. And there's this really fractal quality to this. And when we start getting into what makes up a good API, keep in mind that we're talking on all levels. These principles apply both to the method level, as far down as you can go, all the way up to the framework level. And it's the same principle. And that's the beauty of object-oriented code, is it lets you look at however broad you want to look at. You can go from the widest part of your application to the narrowest part. So let's talk about where we go from here. What makes a good API? And remember, when I say API, we're talking about that entire stack. What makes a good API? A good API does one thing. Preferably, it does that one thing well, but it does one thing. A good API never changes. How many people here have implemented Facebook's APIs? How many people here know what the problem is that I'm saying with relation to this slide? Good APIs are extendable, meaning you can add new behavior to it, but you never change the existing behavior. For a good API, at least. A good API behaves like a contract. If I give you an object that has an add method, you don't expect it to subtract. You expect it to do what it says it's going to do. And a good API has a narrow responsibility. Now, the first one, does one thing and has a narrow responsibility, sound very similar, but they're distinct. Because I can say, my one thing is to emulate Facebook. Wait a minute, I now have a class that emulates Facebook. That's a problem. Here, this is saying it has a narrow responsibility, which means you can pick something broad, but a very narrow part of that broadness. Kind of makes sense? All right. So it also depends upon abstractions. We don't want to depend upon details, because that's what object-oriented programming is trying to get us away from. By abstracting things, we can focus on what we care about and ignore the rest. So what our code depends upon, what we work with, should be abstracted. And that's solid code. That's what the solid principles are, at the root level at least. So we have an acronym, the single responsibility principle. And a good API does one thing. How many people have seen this? How many things does this do? A lot. How many do you think it does well? Well, there is a wine opener over here. I don't know how you would use that. I think there's a pair of tweezers in there that might work well, because they come apart. But the point being that you don't want to have an object that looks like this. Bad, right? God object. You don't want to have a package or a library that looks like this either. It works on all levels. So that's basically the single responsibility principle. Then we go into the open and closed principle, which is, again, a good API never changes. Open-closed principle, it's open for extension, meaning you can add things to it by extending it, but it's closed for modifications. Anything that's designed to work with it now will still work with it tomorrow. If you wanted to put on a hat, do you perform brain surgery? You don't modify your head to put the hat on. You put the hat on and extend. Relatively straightforward. The Liskov substitution principle, which is actually a lot easier to understand than it is to pronounce. A good API behaves like its contract. It does what it says it's going to do. Formally, there's a parent-child relationship. Rather than give you a formal definition, I'm going to give you a real-life example of this. You've seen outlets that look like this, right? The two-prong outlets. These have been around since like 1900, something like that, where you have a plug, you have a 112-volt supply, 112-volt return, or 0-volt return, whatever, neutral, and you plug a plug in, and you get electricity. Great, right? Brilliant. Now we come along, and we're in the 1960s, and we've learned a lot about electrical theory, and we now understand, hey, wait a minute. We need a third pin. We need to provide ground for safety, for efficiency, for a whole lot of reasons. We could do like the Europeans and design a completely brand new connector, or we could apply the Liskov substitution principle, which says we're going to take this format, we're not going to modify it, but we're going to extend it so that the parent still works, the two-prong plug still works, but our new child three-prong plug will work. So we add that third prong. It still behaves like its parent every time you try to use it like its parent. Every time you have a two-prong plug, it behaves exactly the same as the original two-prong. But now we've added the functionality that we need for the future parts that we're going to use in it, the future adapters. We could take it a step further. We could add multi-adapters to where it still works like the parent, it still works like the three-prong, but it also works as a whole bunch of other things. But the point being that the change that we made, the child still behaves like the parent. A good API has a narrow responsibility, the interface segregation principle. Prefer many smaller interfaces to few larger interfaces. Leatherman. Phenomenal tool. The original Leatherman was fantastic. It does many things, but it does many simple things, and it does each one of those simple things well. That's what the interface segregation principle is telling us. We can do multiple things, just keep them separate. Allow them to each do what they need to do. And finally, dependency inversion. A good API depends upon abstractions. How many people here have a set of traditional screwdrivers? You know, you have the handle, and then you have the little bit on the end, and you have a specific size screw, and you need to go hunt for the right one to use, right? Your abstraction, the handle, depends upon the detail of the bit. Instead, we want to depend upon the abstraction. So what can we do? Well, we can do something like this, where the handle depends upon an abstract bit, and then we create details which also depend upon that abstraction. This is object-oriented design. Your handle is one layer of abstraction. It depends upon something else in the middle to translate to the details on the other end. So now we can swap the handle for a screw gun, use the same bits. We can swap the screw gun for an automatic drill. The point is the abstraction still holds. This is a good abstraction. Makes sense? That's solid. That's all there is to it. Now, one thing I want to point out here, solid does not dictate what good object-oriented code is. It wasn't some people, smart people sitting up in a room going, you know what, object-oriented code should be this, so let's make these list of 5 rules, and we're going to call it solid and make everybody abide by it. Solid emerges from good OOP. When you start writing OOP for a long time, as you start really experimenting with pushing the boundaries of object-oriented code, you start to notice these patterns developing under the hood. You start to notice that simple, lightweight objects are better. You start to notice that objects that do one thing are better. You start noticing that depending upon details winds up hurting you in the long run. So solid really is an evolution of object-oriented design as opposed to being the set of principles that we apply and we leverage. So try it, play around with this code, play around with these philosophies. It does make sense, and you can always take it a step further. So that's good API design. Let's talk about bad API design for a minute. And now we're going to get into something else. So using global variables. How many people here think global variables are good? How many people think they're bad? Very good. They serve a purpose. There are times you're going to need global variables. The point being here, in object-oriented design, they are bad. There's going to be parts of your application where you can use them, but for the most part, we call it spooky action at a distance. There's a great video by Misko Heverly, who's a Google engineer, where he talks about unit testing. And he tells this story that when he first signed on, not to Google for one of his prior jobs, he winds up having to test a store, like an e-commerce store. So he goes up and he creates this shopping cart, and he enters his credit card details because he just needs something that looks like a valid credit card. And he puts a $1 item on, and then he runs the test, and the test passes. And he goes, okay, sounds good, I'm done, right? Walks away. About a month later, he looks at his credit card bill, and he sees several $100s worth of transactions. And he goes, wait a minute. I just created a shopping cart. I didn't give it a payment gateway. I didn't give it any details on how to complete this transaction. And just hitting save on this, or just hitting buy on this item charged my credit card. That is weird. And you start digging through, and it turns out that it was using singletons and using global variables to create a new payment gateway, which he's labeled spooky action at a distance. You do something here, and something unrelated over here changes. That's bad. That's not what we want to see in object-oriented programming. Depending upon specifics of an implementation, we're tight coupling things together. We don't want to do that. We want to depend upon abstractions. When we have hidden dependencies in our code, that's a very bad thing. And that, again, a lot of these are very closely tied because a form of hidden dependency can be a global variable. An unhealthy focus on performance is bad. Premature optimization is bad. When you do it, we can talk about, but we don't want to get too heavy into prematurely optimizing. Poorly named APIs are bad. If your class has a method run, it better be describing a runner. What does run do? Your method name coupled with your class name, coupled with your package name should tell a story. And duplication. Duplication is the enemy of good code, right? So that's stupid. Singletons. So did some research on this, and the story behind Lord of the Rings, I think, is exceedingly good here, because, and I'll do this really quick and as a 30-second aside. If you don't know the backstory, like if you haven't watched the first movie of the Lord of the Rings trilogy or read the books, the basic premise here is this evil Dark Lord Sauron crafted these rings. He gave a bunch of them to the elves, a bunch of them to men, and a bunch of them to dwarves. And he gave them these rings of power as a token of goodwill. But secretly, he crafted this ring, the one true ring, the ring of power, to bind all of those and give him control over everybody who was wearing those other rings. The reason that this is a great example is it's spooky action at a distance. These people were wearing these rings, these elves were wearing these rings, thinking that they were providing power, and they were. But in secret, they had this other hidden purpose that they only learned about later when everything went bad and bad things happened. Singletons are evil in object-oriented code. If you're not writing object-oriented code, singletons are very, very helpful. And they can be useful. And I think that's a leap that people often refuse to make. Not everything has to be object-oriented. There are other paradigms that work very well. So the T is tight coupling, and we talked about this. So if we're building a race car, we can custom make an intake manifold, right? We can fine-tune everything, and we build this car, and then we go out to the racetrack, and then the part breaks. What do? You're tight coupled to this part. Whereas if you use something off the shelf, you can just swap in a new one. We don't want to be tight coupled. We want to loosely couple. We want to couple upon abstractions. Untestable code. Sounds great, right? How many people here unit test? Okay. How many of you always 100% of the time have 100% test coverage? Good, thank you. So there's an example I love, and I'm a science geek. I'm definitely a geek at heart. Lunar lander. I use this for talking about untestable code because there's a fact about this I think is fascinating. The engine that this uses has exactly two moving parts. There are two valves. It uses what's known as a hypergolic fuel, which basically means it has an oxidizer and a fuel source that when they open the valves, the two mix in the combustion chamber and they ignite and they explode. So incredibly reliable, ridiculously reliable. As long as those valves open, that engine fires and they go home. Also comes with a slight problem. And that slight problem is those fuels are highly, highly, highly corrosive. To the point that after you fire an engine, you have to throw it away and build a new one. So now think about this for a minute. The first time that this engine ever ran, ever, was on the surface of the moon. Imagine you're the engineer responsible for designing this. Imagine you're the engineer responsible for building it, for actually assembling it. Think about that pressure. Now, in this case, the benefits to it were worthwhile, and that's why they chose to do it. They did a risk analysis on it, and they said that the reduced complexity of this system to have two moving parts is worth the potential impact of not being able to test those parts fully. Chris Harchis will probably yell at me for saying this, grumpy programmer on Twitter. 100% unit test coverage is a lofty goal. It's, I don't think, a practical goal. Instead, what you should shoot for is testing everything adequately. That doesn't necessarily mean 100% coverage. It means taking enough precautions to where that code is tested safely. So in this case, all right, let's say we're going to create a system where we're going to pump water through this engine, and we're going to test those valves using water. Sounds reasonable. Yes, it's not a fully running engine, but you're kind of putting two and two together here. We're trying to limit our potential liability while getting the biggest win that we can. And some systems that you're going to build, you're not going to be able to test. And that's okay. Do what you need to do and get far enough where you're doing the right thing. So premature optimization, we talked about that briefly. If I want to build a motorcycle, and I say, oh, I want to build a fast motorcycle, you don't start with a Dodge Viper engine. This thing will do 300 miles an hour, but can't turn a corner. Focus on the correct optimization. If you're designing a fast motorcycle, You start with a engine. You start with a fast engine, but you don't optimize that engine until you build the rest of the bike. And that same thing comes with object-oriented design and programming in general. Don't try to resist optimizing before you have something built. Make decisions based on where you need to go, but don't go deep into the optimization until you have a whole that you can work with. And indescriptive naming. This one, do I really need to go too deep on? Would you drink this? Try to describe what you're doing adequately. Yeah. And duplication. Everybody know why duplication is a bad thing? Yeah? Okay, good. Copy and paste all the things, yay. I'll actually interject a note here. I don't follow dry religiously, the don't repeat yourself rule. I follow what I term as the rule of 3, which is basically copy and paste once. Because the first time I need to duplicate code, I normally don't know enough about that code and about the situation to be able to effectively refactor. So I'll copy and paste once, and then the second time I need to do it, the second I need 3 copies, that's when I stop and force myself to revisit and refactor. Because normally I find rule of thumb, 3 copies tends to give me a better picture. Try it out. You may like it, you may not. So that's stupid. So stupid embodies lessons learned from bad OOP. Unlike solid, stupid doesn't just magically fall out when you do it right or when you do it wrong. It's just people who've been doing this a long time have tended to notice that these stupid principles lead to bad code. Does anyone object to any of those principles? Feel free, do it now. No? Okay, good, thank you. So OOP gives you a whole bunch of these things. It gives you code that's modular, where now we can reuse it, where we can treat code as this block. It gives arguably easy to read code. It gives you maintainable code because now you're depending upon abstractions, so you can swap out the things on either side of that abstraction and think that things should work. Gives you easy to understand code. And easy to read and easy to understand are 2 different things. But OOP isn't a perfect solution. It costs you a lot too. It tends to have more layers. You know, we've all heard of spaghetti code, where you have procedural code that just nests of ifs and fors and garbage. In OOP, you can get what's known as lasagna code, which is just layer upon layer upon layer upon layer upon layer. It tends to be slower at runtime. Now that one I really want to caveat by saying it's slower at runtime, but it's still fast enough for your usage most of the time. So you can measure a difference, but for the most part, you're talking microseconds. You're not talking, you know, going from 1/4 of a second procedurally to a year in OOP. You're talking very, very small differences in speed, but measurable. Tends to result in larger code bases. Some people see that as a negative. I see it as a positive, because if you have better abstractions, the larger code base means you can only focus on smaller parts at a time. But it is a legitimate potential cost. The other one I want to really talk about and nail home here is that it tends to require more tacit knowledge. I give you an OOP code base that you've never seen before. Chances are it's going to take you longer to read it, because you need to start figuring out what conventions did I use? What terminologies am I using? How am I abstracting things? You have to read documentation. Hopefully I wrote documentation. I'm not really that good at that. The point being that OOP does have a lot of mental overhead. But once you get past that mental overhead, it tends to let you ignore and focus on thin abstractions and focus on the parts that you really care about. And that's why people like me preach for OOP. So let's look at some code. And this is going to be really simple, really high, but let's imagine we want to build a robot that's going to drive our car. What would the public API of that robot look like? Well, we could build this interface car, because it's interfacing with the car, which is badly named. It has turn left and turn right methods. Okay. It also has a go faster and a go slower method. Why is turn right and go faster on the same object? It has shift up and shift down. Okay, I kind of maybe see where that's going. and it has this other method, start. Seems like a weird grouping. I mean, yeah, they're all car-related methods. They're all methods that you would expect your car to have, but turn left and turn right is very different action than accelerating and decelerating. And it's even more different than shift up and shift down, and it's completely unrelated to start. So if we compare stupid here, singletons, we don't know. We don't care about that. We have duplication, turn right and turn left. We could probably refactor that to one method. We have indescriptive naming. What does turn left really mean? Are we turning the wheel full left? Are we turning the wheel a degree? Are we turning left relatively or absolutely? The point being here that if we went through solid and stupid, we would see that this interface looks like a bad interface. So we could refactor this. Let's break it apart into 3 different interfaces. We have a steerable interface, which means I can turn left or right, and I can pass it an angle I want to turn. Is it perfect? I don't know. It depends on what we need, but the point is it's specific. It's small. It does one thing. Acceleratable interface. We can accelerate. We can pass in a positive value to go faster. We can pass in a negative value to go slower. We have one thing to interact with. Shiftable. We shift up, we shift down. What happens if you're driving an automatic? That doesn't make sense. So now you don't have to implement that interface. If you're modeling an automatic car, you don't implement shiftable. You're done. You don't have to worry about it. You don't have to fake and kludge things to get it to work. And that's the point of these principles, really to separate out and think about your abstractions in the context of how you're going to use them. No stopping in here. Wait, what? Hey. So we can also, this slide is supposed to not be here, but okay. I'll talk about it anyway. So we can have this transmission concept too, where you have the base transmission, which defines what all transmissions do, and then you have different types of them that allow you to shift in different ways and that interact in different ways. So the cool thing is you could have an automatic transmission that you decorate to make it look like a manual. So you could provide Tiptronic shifters, like the paddle shifters, on an automatic that look like a manual. The point being is by looking at the abstraction and looking at what you need the abstraction to give you, you can tune it to what you need. So there's one final principle I want to talk about before we're pretty much out of time, which is the principle of good enough. It was the very first blog post I ever wrote on my blog, and it's a concept I think that we don't focus on enough in this industry, which is to say, if it gets what you need to get done, it is a good thing. If you're a hockey fan, there are good goals and there are bad goals. There are pretty goals and there are ugly goals. But what matters is if that puck crosses that line. That's what matters. In the business sense, does that application deliver business value? Yes or no? That's what matters. We can sit here and talk about better methods and the best method and good methods and bad methods and anti-patterns and patterns and pros and cons. At the end of the day, it's up to you to deliver business value. At the end of the day, if it works, it works. We want to strive towards good and towards best, but we also want to be realistic enough to know, hey, you know what? If it works, it's good enough. Don't hyperly focus on the latest, greatest. Don't hyperly focus on the bleeding edge. Focus on what you're comfortable with and understand the trade-offs. Thank you. Okay, questions? Yeah. Here. Yeah, wherever. So, okay. Mic situation. You okay?
Thank you. I know PHP 5, 3 or 4 has type hinting signatures. Can you do interfaces? That's just
5.0 does. Yes. So the question.
With this, you'd require like a manual transmission interface. Like,
Yep. So the question was, with PHP 5.3 or 5.4 allowing you to do type hinting, can you type hint against an interface as well? Type hinting has been in since 5.0. And yes, you can do interfaces, and that's actually the preferred method, is to put in interfaces what you require. So you're depending upon the abstraction. Give me this abstract concept and leave it up to the caller to determine how to do it. So yeah, absolutely. You had a question up here? Up here, right here. Yeah, sorry.
Yeah, so that example that you gave really helped out, like, 'cause I was sort of seeing things abstractly. One thing that still kind of confuses me is figuring out, like, I can see how shift up and shift down and turn left and turn right, all of them together packed in that one interface. After you showed that example, I can see how that makes more sense. But how do you come to that conclusion? Like,
Okay.
that's the part that kind of confuses me.
So the question, and I'm basically re-saying everything for the recording. The question was basically, yes, it makes sense once you get to the split out interfaces when we're talking about the car. It makes sense once we get to this point, but how do we get to this point from here? The way that I would say it is refactor, refactor, refactor. So you start building this, and it may suit your purposes. And if it suits your purposes, great. You don't need to go to that next step. But you're going to, more often than not, run into pain. You're going to start seeing things that, hey, you know what? I've got to work around the fact that I have separate go faster and go slower, and I wind up having all this duplication of my code because those two methods are separate. And then you can start to say, hey, wait a minute. If I combine those into one method, that makes life easier. So you combine it into one method. And then later on down the road, you start looking at, you have to implement something that isn't steerable. You want to implement that motorcycle that we saw, which only has a accelerate method. It doesn't have a turn left and turn right method. Now you can actually extract that interface and say, I'm going to separate interface car from interface acceleratable. So it really comes down to focusing on what your requirements are. What are the needs of that application? And focusing on refactoring a working system.
One more question.
Yeah.
Another thing I noticed is that, like, with interface car, for example, you're describing an entity, and like with like something like steerable, you're more describing the capabilities of the car.
Perfect. Well, okay, remember back at the very, very beginning, the first couple slides I talked about, the old classic model of object-oriented programming is to talk about things. Interface car describes a thing. The new model, the modern view of object-oriented programming talks about behaviors. These are behaviors. It behaves as something that's steerable. It behaves as something that's acceleratable. And that's the difference. It's just a different conceptual way of looking at it. Okay. There's a question over here. Yes. And then back to you next.
Just a follow-on question.
Yep.
As you said, refactoring, it
Yep.
takes time, always takes time, and that's maybe not related to the topic, but how to convince your boss that you need to refactor your code?
How to convince your boss that you need to refactor your code. If your boss doesn't listen to you, then that's a bigger problem. I say this to any developer that I have that's working for me, when I had teams working for me. I hire you not because I want you to do work. I hire you because you're smart, because you're an expert in your domain. Even if you're a junior developer, you're still an expert within that domain, and we hired you because you're representing that domain. So if they're going to hire you to do work and then tell you how to do that work, why are they hiring you? So that's the idealistic view. The practical is I build that in. So I refactor consistently from the second I write code. I'm kind of half working on a new talk / blog post / book where the concept is dirty code. And the way I start that is I write the dirtiest, most piece of garbage code I can that solves a problem. So if I have a feature I need to build, I build that feature as quickly, dirty, and cheaply as possible. And then I refactor. I don't consider it done. It works, but I refactor and I refactor and I refactor and I keep refactoring until I'm happy enough with where it is that I think that that is both good enough and suits that need. So really, I would just do that as part of your task. It's not a separate task. You know, testing is not separate from writing code. Refactoring is not separate from writing code. They're the same process. They're just steps in that process. As far as dealing with legacy code, good luck. So question all the way in the back. Here, he's been waiting for a while, if you wouldn't. Yeah.
I'm just kind of curious. Sometimes I get a little mixed up trying to decide whether to use an abstract class or an interface. And I don't know if there's some
Okay, the way I would do this, the question was, how do you decide when to use an interface versus an abstract class? The way I say it is, if I think I need to use an abstract class, I'm doing something wrong. I do wind up practically using them, but I use them from a good enough perspective, realizing that I'm making a conscious compromise to get code on the ground that's working. I always prefer an interface. So, and then we'll do two more. You had one, and then.
All right, so my question is, based on, during the presentation you said that singletons don't have a place in OOP.
Correct.
Can you elaborate?
Singletons don't have a place in OOP because it's global variable. So the way I can describe it is this. You create a singleton for two reasons. One, because you only want one copy of an object. Well, if you only want one copy of an object, instantiate it once. Why is it your object's job to enforce the fact that there's only one of them? And the second one is because it's easy to access globally, that if you need a database, you don't need to pass it into this class. You just use it, right? And it seems really good and really easy, except that that creates that spooky action at a distance we talked about. Global variables, global binding. You can do it, and so I'm a firm believer that everything is a triangle. You have procedural programming, functional programming, and object-oriented programming. And all the code that we do lies somewhere on that plane. So you can have a mix of procedural and object-oriented, which I term as class-oriented code, which is CodeIgniter, which is Cake. They're procedural code that uses classes. It's not really object-oriented, and you can get object-oriented code that doesn't use classes. But the point being that the singleton itself isn't a problem. It's when you try to use a singleton with object-oriented code, that's when you start running into problems. Kind of makes sense? Kind of? Okay, and then last question over here.
It was a follow-up actually to this point
Okay.
about abstract classes. Wouldn't you think that sometimes abstract classes are justified to avoid duplication?
So do I think that abstract classes are justified to avoid duplication? Yes. That's the way I use them in practice. However, I use them as a realization that PHP is not expressive enough to deduplicate via composition purely, and that I need to have inheritance to do that deduplication. So it's an effect of me not being happy with a refactor as opposed to a direct consequence.
Well, traits do help a lot.
Traits help a lot. Traits hurt a lot too, though, because traits are static composition. So, okay. Thank you very much.